Last time we looked at the water model on the complete graph, and we worked out the probability that the agents reach consensus on uh, either of the two opinions. This time we are going to look at the water model on an arbitrary graph and look at conditions under which consensus is reached, and then work out the probability of it being reached on a specific initial value. So let me start by sharing screen. Okay, so first I'm going to introduce the water model on a general graph. As before, we have a set of n agents. Agents will be identified with the vertices of a graph. So G is a graph with vertex set V and edge set E, and the vertices can be thought of as agents. Each agent can hold one of two possible opinions or preferences, which we'll denote by 0 and 1. And they start with some initial preferences, which they are going to update through interactions with each other. We introduce the water model on the complete graph by specifying these interactions through a two-step process. So first we specified a node-centric view. We put clocks on nodes and then use these to define the process. But we also showed both for the water model and before that in rumor spreading that the node-centric viewpoint is equivalent to a certain edge-centric viewpoint. And this time we are going to just go ahead and directly define the whole model from an edge-based perspective. Okay, so let's do that. With each directed edge VW, we associate a Poisson process, n subscript VW. And this Poisson process has intensity QVW. And there's one such Poisson process for every directed edge VW. Okay, and these are all mutually independent. And the graph comes in by saying that the rates, the intensities of these Poisson processes are 0 if VW doesn't correspond to an edge. Okay, so equivalently, this Poisson process is empty if there is no edge. Okay, so we'll also define QVV to be such that the row sums, so we'll define a matrix Q whose off-diagonal elements are these intensities of the Poisson processes. And we'll set the diagonal elements in such a way that the row sums are all 0. And recall that any matrix with that property, that the off-diagonal elements are non-negative and the row sums are 0, is the rate matrix or generator of a Markov process. Okay, so this is a Markov process whose state space is V, the set of vertices. And so we are defining rates for moving from one vertex V to another vertex W. So this is some Markov process unrelated to the water model. We'll come back to this later. But now let's go on to define the water model itself. So we have these Poisson processes with these intensities QVW associated with the directed edges of the graph. And the interaction is going to be as follows. Whenever this clock rings, this Poisson clock NVW rings, meaning whenever there's an increment or a jump in this Poisson process, then V contacts W and copies the opinion of W. Okay, so V makes a phone call to W and copies the opinion of W. So this is the pull model, and we can define the push model the same way. Okay, take a moment to make sure that you fully understand the model. I've specified exactly how the water model evolves, starting from an arbitrary initial condition. Okay, so let's move on now from that verbal description of the water model to a Markov process description, which we can then use to analyze its behavior, its long-term behavior. So we'll denote the opinion of agent V at time t by x sub v of t, and this can either be 0 or 1. Those are the only two possible values this can take. And we'll denote by boldface x of t the vector of these opinions of the agents. Okay, so it's the vector xvt indexed by v in the vertex set. And we call this the configuration of opinions at time t. The claim is that this vector evolves as a Markov process. The state space is 0, 1 to the v. The set of all possible vectors is vectors taking values 0 or 1 and indexed by the vertex at v. Okay. And we claim that this is a Markov process with the following transition rates. So the rates I'm now denoting by eta. We usually used to denote it by q, but we have defined q to be something else, and I want a different letter. So this is eta. And the rate of going from x to x plus ev, ev is the vth unit vector. It's a 1 in the vth position and zeros everywhere else. So this says that the vth coordinate of x increases by 1 and all other coordinates stay the same. So what's the probability this can happen in a small time interval delta? What needs to happen for this change to occur? Okay, so the only way that any vertex changes its opinion is by contacting another vertex. And here we want the vertex v to change its opinion. That means v has to contact some other vertex w. And what has to happen to vertex v? If it was already in state 1, it cannot move to state 2 because the only possible values are 0 and 1 for a vertex. So this change can happen only if xv was 0, the v coordinate of the vector x was 0. Okay, so we need that the indicator of that event. Now, if v starts with opinion 0, it can change to opinion 1 by contacting some vertex in opinion 1. So we sum over all vertices w in opinion 1, the rate at which v contacts w. Okay, so which is qvw. So in some very small time interval delta, the Poisson process on the edge VW sees an increment with probability QVW delta, because that's the intensity of the Poisson process. And if there's an increment, then V contacts W and copies the opinion of W, which was a 1. So V changes its opinion from 0 to 1, meaning that this coordinate changes from 0 to 1. And this could have happened by copying any vertex in state 1. And so we add up these probabilities. More precisely, we have to subtract the probabilities that 2 of those events happen, add back that 3 happen, etc. But all those are probabilities, delta squared, delta cubed, and so on. So we are ignoring them. So the dominant term is the QVW delta term times delta term for the probability. So thinking of these as probabilities, this whole thing on the right-hand side is multiplied by delta. So in some small time interval delta, The probability of going from x to x plus EV is this whole thing times delta, which means that the rate is exactly this. Okay, again, make sure you understand that. Make sure you understand the distinction between probabilities and rates, and how to write down rates from a verbal description if you like thinking through probabilities. Okay, so that's the rate of going from x to x plus EV. Similarly, the rate of a transition from a configuration x to the configuration x minus EV. Well, how can this happen? Then the vertex x should have had a 1 in the weak position, which changes to a 0. And for that to happen, V has to contact a vertex with opinion 0. So we sum over all such vertices the rate for V to contact such a vertex W. Okay, so these are the only possible transitions of this Markov process. In a very small time interval, only one coordinate can change at a time because two things don't happen in a Poisson process simultaneously. Okay, so these are the rates. What else? So why is it a Markov process? It's a Markov process because if you know the configuration at some time t, how you got to this configuration doesn't matter because the process is built. The process xt is constructed on top of Poisson, independent Poisson processes. And these individual Poisson processes are memoryless, so something constructed on top of them depends on the past only through this current state x, and not on how we got to this state. Okay, so if you've convinced yourself that xt is a Markov process and these are the transition rates, so then we can go on to ask, how does this Markov process behave in the long run? In particular, it's easy to see that the all 0 and all 1 configurations are absorbing states. So if all the coordinates of x was 0, what's the rate of changing one of them to a 1? The sum here is empty because there are no vertices in state 1, and empty sum is 0, so the rate is 0. So that's one way to see that once you get to state 0, all zeros, you get stuck there because the rate of any transition out of that state is 0. Also, more intuitively, nobody can change their opinion to a 1 because there are no ones to copy. And similarly, the all 1 configuration is absorbing. Okay, and they are also, are these accessible from all other states? Yes, provided every node can influence every other node. And that's guaranteed if the graph is strongly connected. So, so when are these configurations not accessible from all other states? So let me give you one counterexample. Suppose the graph consists of two disjoint pieces. So a fully connected piece here and a fully connected piece here, and no edges between them. And suppose you start all these vertices in this piece in state 0 and all the vertices in this piece in state 1. Well, these are two disjoint communicating classes, so this will forever stay in state 0, this will forever stay in state 1, but the whole graph won't reach 0, won't reach 1. Okay, so that's intuitive. So that's a counterexample to reaching consensus. And that's more or less it. Okay, so anyway, so clearly consensus will be reached if every node can influence every other node. And then these configurations are accessible from all other configurations. And this is a sufficient condition to guarantee that consensus is reached. Okay, so what are we interested in? So we are guaranteed to reach consensus on the all zero or all one configuration, and we want to work out what the probability is of doing so, say on the all one state, given the initial condition. In order to analyze that, we are going to have to look at an auxiliary Markov process, which I'm going to introduce now. And this auxiliary Markov process is the random walk on V with rate matrix Q. So there are two processes going on here, and don't confuse them. There's the voter model, which is a Markov process. The voter model is a Markov process on the configuration space, the space of all configurations, and that space is 0, 1 vectors indexed by V, which you can equally think of as subsets of V. And this is a state space with 2 to the n states. If the cardinality of V is n, then the number of all such vectors is 2 to the n, or the number of all subsets of V is 2 to the n. So this is a Markov process on a big state space. And we are going to analyze this Markov process using an auxiliary Markov process, which is a random walk on the vertex set. So that has states. The state of the random walk is the position of the random walk at time t. And so the position is some vertex in the vertex set, and there are n vertices. So this is going to be a Markov process on the much smaller state space of cardinality n. And we define this random walk to have this rate matrix or infinitesimal generator Q, meaning that in some small time delta, if the random walk is in state V, it moves to, if it's at vertex V, it moves to vertex W with probability QVW times delta. Okay. Okay, and so the edge set, I'm just writing that we'll identify the edge set as the set of all directed pairs of vertices for which this rate is strictly positive. Okay, and we saw, by the way, strongly connected. I mentioned this already on the last slide. So we say that a graph is strongly connected if for every pair of vertices V and W, there's a directed path from V to W and a directed path from W to V. Okay, so thinking of the edges as one-way roads, it's possible to go from V to W, and it's also possible to go from W to V. Okay, and so if the graph is strongly connected, then the random walk is irreducible. You can get from any vertex to any other vertex. And it's Markovian because we defined it to be such on the state space V. Okay, and so we know this is a finite state Markov chain. It has an irreducible, it has an invariant distribution. It's an irreducible Markov chain, so the invariant distribution is unique. And so let's denote by pi the unique invariant distribution of this Markov chain. I'll use the terms Markov chain and Markov process interchangeably. Okay, and now the claim is that if we define mt to be this, so you should think of pi as a row vector and xt as a column vector. And so mt is the product of this row vector and the column vector, and that gives you a number. The claim is that mt is a martingale with respect to the history of this process xt. up to time t. Okay, filtration is just a fancy word for history. Okay, so this is the most important result in the analysis. So before we move on to proving this lemma, make sure you understand the statement of the lemma and all the terms that go into defining it. So we have a voter model, which is a Markov process on the configuration space. Its state at any time t is a vector of length n. So the elements of the vector are either 0 or 1. And you should think of the elements as being indexed by the vertices of your graph. Okay, so that's the voter model is one Markov process on the graph. Another Markov process is a random walk on the graph. So this is a Markov process whose state space is the vertex set, not the set of configurations, just the vertex set. And under the assumption that the graph is strongly connected, which we'll make from now on, this random walk on the vertex set is irreducible. It's a Markov process, so, and it has a unique invariant distribution, which we denote by pi. So pi is again a vector indexed by the vertex set. Now this is a vector whose elements are non-negative and they add up to 1. It's a probability distribution on the vertex set. And you should think of pi as a row vector. You should think of the configuration at any time t, which we denote by boldface x of t, as a column vector. So if you multiply this row vector pi and this column vector xt, you get a number for each t, and that's what we call mt. And the claim of the lemma is that the process mt is a Martingale. Okay, and that's what we are going to prove next. Okay, what do we have to prove firstly? So we want to prove, to show that MT is a Martingale, we want to show that over some very small time interval delta, the expected change in expectation between MT and MT plus delta. So if you look at MT plus delta minus MT, the expected value of this difference, the conditional expectation, given the history up to time t, the conditional expectation of this difference is little o of delta. It's close to 0. Okay, that's what we want to show. In terms of the definition, we want to show that the change in expectation of MT over finite-sized intervals conditional on the past is 0. And the way we are going to show that is by showing that over infinitesimal intervals, it's essentially 0. It's little o of delta. But remember that it's conditional expectations we need to calculate and conditional expectations given the past. So for every possible history, we want to look at the change in conditional expectation. And there are infinitely many possible histories, so that seems like an impossible task to achieve. But because xt is a Markov process, the history is summarized by the current state. So we only need to show that the change in expectation conditional on any given state. So if I tell you that xt equals x for a specific x, then you have to show that the change in expectation is 0 no matter what that x was. Again, let me repeat what I've said. It's important to show that the change in conditional expectation is 0. You're not calculating the change in expectation of MT, you're calculating the change in conditional expectation. And this has to be calculated in principle for every possible history. But in practice, that works out to simply calculating it for every possible state in a finite state space because of the Markov property of xt. Okay, so let's do that calculation now. So let's suppose that the Markov process boldface x, the configuration of the voter model at time t, is little x, again boldface. So this is a 0, 1 vector indexed by v. Then what are the possible choices at time t plus delta? It's x plus ev. With this, we already worked out the rate for the Markov process. I'm just multiplying that by delta to get the probability. And then there's little o of delta corresponding to 2 or more jumps in this process over the small time delta. But those are vanishing as delta goes to 0. At least they are vanishing faster than delta. Sorry, this should be a t minus delta here rather than tau. This is a typo here. Similarly, the t plus delta, not t minus delta, t plus delta again here instead of tau. So the probability that at time t plus delta, the voter model is in configuration x minus ev is again given by the rate of jumping from x to x minus ev times the length of the time interval, which is delta plus little o of delta. Okay, so these are the possible changes in configuration over a small time delta. From your initial condition x, you can either go to x plus one unit vector corresponding to the vth element, or x minus the same unit vector. And how does the value of the Martingale change? So what happens to m of t plus delta? Recall that m was defined as the row vector pi times the column vector x. So if x increases by 1 in the vth position and all other elements stay the same, then m increases by pi v, the vth element of the row vector pi. Similarly, if x decreases by 1 in the vth position, m decreases by pi v. Again, tau should be t plus delta. Sorry, all these taus should be t plus delta. Those are all typos. Okay, so that's the change in the value of the Martingale over some small time delta. And we know the probability that m increases by pi v, it's this, and the probability that it decreases by pi v is given by this. And so we can calculate the change in expectation. It's the change in value multiplied by the probability of that change. So the expectation of mt plus delta minus mt, given that the voter model was in configuration x at time t, is delta times the sum of these rates. So I'm skipping some steps here. I should fill in some missing steps, which I thought were already there. Okay, so let me stop sharing that and share my whiteboard. Okay, so we have xt goes from x, the vector x, to x plus ev at rate, just copying this down, sum over, okay, I should put in the indicator that xv is 0, sum over W such that XW is 1 of QVW, and it goes to X minus EV at rate the indicator that XV is 1, the sum over W such that XW is 0, QVW. Okay, so if we want to calculate the expectation of MT plus delta minus MT, given that XT equals X, I don't know if XT was this way, equals X. And I also give you everything about the past. So I tell you XS for 0 less than or equal to S less than or equal to T. By the Markov property of X, all this is irrelevant. All that matters was that XT equals X. And the changes in expectation is, okay, for a given vertex V, it's pi V times either this sum, if XV was 0, or it's minus pi V times this sum, if XV was 1. And then we are summing over all vertices. So let me split up that sum into two sums. So this is the sum over vertices V such that XV equals 0. And then we have this sum up here of W such that XW is 1 of QVW. So let me write that. So then we have the sum over W such that XW equals 1 QVW times delta. QVW was the rate. QVW times delta is the probability of this change happening in time delta between t and t plus delta. And then we saw that if V changes from 0 to 1, that increases the value of the martingale by pi V. So we multiply by that. So this is the change in value of the martingale. Alternatively, a vertex could flip from state 1 to state 0. So we add now over all vertices V in state 1. And these flip if they contact a vertex W in state 0, QVW. Okay, so for a vertex V in state 1, this was the rate of going to state 0. So that's the rate. And for a particular vertex V in state 1, and then I add up over all such vertices, and whenever one of them flips to state 0, okay, and this was the rate, so the probability is, I need to multiply this by delta, and the value of the martingale decreases by pi V whenever V flips from state 1 to state 0. Okay, So this is the change in value of the martingale over a small time interval delta. And let me also put in the plus little o of delta for completeness. So that's to be ignored. Okay, so that's the sum. And now I'm going to add and subtract something. I'm going to add and subtract the sum over v such that xv equals 0 and w such that xw equals 0. Okay. So here we had a sum where xv was 0 and xw was 1, and here xv is 1 and xw is 0. So I'm going to add where both xv and xw are 1. And if I add that, so I have now the sum over v such that xv is 0. And for each vertex v, I have here the sum over w such that xw is 1 of this term. I'm also adding the sum over w where xw is 0 of the same thing. So I've added it over all possible w, whether it's whether xw was 1 or 0. So I'm left with the sum over w, q v w, pi v, delta. Okay, minus similarly, I can now interchange the order of summation. So let me first do the sum over w of xw equals 0 times the sum over v. Now here I had the sum over v xv equals 1, but because I added here the sum where both xv and xw were 0, I have to subtract the same thing there. So with the minus sign, I'm adding a sum over v where xv is 0. Okay, so xw is 0 is taken outside. I'm adding over v such that xv is 1, and I'm also adding over v such that xv is 0. And that means I'm adding over all possible v, whether xv was 0 or 1. And so I end up now with the sum over v, the same thing, pi v q v w delta. Plus the little of delta. Okay, so in both cases, now let's look at the inner sum. I want to focus on this inner sum here and this inner sum here. Okay, so what do we have here? We have this is equal to, we are summing over w, pi v and delta don't depend on w, so let me pull them out of the sum. So we have delta pi v times the sum over all w of q v w. Okay. So this is the sum of the vth row of the Q matrix. And this matrix, by definition, has all its row sums equal to 0. Okay, because this is the vth row sum of Q. Okay, so this sum is 0, which means this whole sum here is 0, which means we are adding up a bunch of zeros and everything here is 0. So the first term is 0. Now let's look at the second sum here. So it's just delta. We can pull out delta again. So it's delta times the sum over V of QV, pi V QVW. Okay, what's that? So this thing here is the vth element of the row vector. So we have a row vector pi, a matrix Q. We multiply the row vector by the matrix and take its vth element, and that's exactly what this is. This is just the matrix multiplication formula. This is just the vth element of pi q. But what is pi q? Pi is the invariant distribution of the Markov process of the random walk with rate matrix Q. Okay, so pi is the invariant distribution of a Markov process with rate matrix Q, which means it solves the global balance equations, but the global balance equations say that pi q is 0, is the 0 vector, or each of its elements is 0. Or maybe you just recognize these, the sum as the global balance equations. And this is saying that this should be 0. Okay, so similarly, this sum is 0 and this whole thing is 0. And all we are left with is little o of delta. And that shows that MT is a martingale. Okay, I hope that calculation was clear. If not, go over it once more, and it's also in the lecture notes. I'm going to, in the printed, not in the lecture slides, it's also in the lecture notes if you want to go through this. So I'll stop sharing the whiteboard and go back to sharing the water model. Okay, so this was the calculation we just did. Okay. Hopefully with that more detailed explanation, you can work through this and see I'm doing exactly the same thing here. The sum was over xv equals 0, xw equals 1, minus the same with xv being 1 and xw being 0. I added and subtracted terms corresponding to xv and xw both being 0. I think, yeah, both being 0, and that gave me this sum. Okay, and each of these is 0 for the reasons I just explained. Okay, and so we get that the expected value, change in value of the martingale over a time interval, an infinitesimal time interval of size delta, conditional on being in state x at time t. These conditional expectations are all little o of delta. And that shows that the process MT is a martingale. Okay, so we define this process MT somewhat mysteriously by taking an inner product of pi and xt. It'll become a bit clearer in the next lecture why we chose that, but given that we somehow define MT that way, what we've shown is that this process MT is a martingale. And now we are going to use this fact to work out what the probability is that the water model reaches consensus on the all-one state, let's say. Okay, but before that, let's work through a couple of examples. So let G be a connected and undirected graph with vertex set V and edge set E. And QVW is going to be 1 over the degree of V. So if this choice of rates becomes very natural if you start from a node-centric model. So each node becomes active at the jump times of a rate 1 Poisson process, independent of all other nodes. And when it becomes active, it picks one of its neighbors uniformly at random and copies the state of that neighbor. So vertex V has degree V, number of neighbors, so it picks any one of them with probability 1 over the degree. So if W is a neighbor of V, then the rate at which V contacts W is 1 over the degree of V. Okay, so these are the contact rates for the water model, and we wanted to study the random walk with this generator. And because the graph is connected, it's possible to walk from any vertex to any other vertex, which means that the Markov process with this generator, the random walk with this generator, is irreducible. It can reach any vertex from any other vertex. Okay, and the claim is that the invariant distribution is proportional to the vertex degree. So the invariant distribution pi, the vth element of that row vector, is the degree of v divided by the total, 2 times the total number of edges. So this is the normalization you need to make this a probability distribution. You can check that if you add up all the degrees, then you get 2 times the number of edges, because each edge is counted in the degree of each of its 2 neighbors, each of the 2 vertices it connects. Okay, so this is the claim. So let's prove this. The proof is easy, and you guess that the random walk is reversible, and check that it satisfies the detailed balance equation. So what are the detailed balance equations? They say that pi v times q vw, the invariant probability of the state v times the rate of going from state v to state w. And for the random walk, the states are the vertices. So this should be the same as in the reverse direction, the invariant probability w times the rate of going from w to v. Intuitively, this is the rate of observing jumps from v to w in forward time. And that should be the same as the rate of observing jumps from w to v in forward time, because when time is reversed, the jumps from v to w become jumps from w to v, and vice versa. Okay, so you can check that this given pi v satisfies these equations, where q is given by this, and therefore we know that pi, if any probability distribution which satisfies the local balance equations, is invariant. And so this is invariant. It's connected. So there's a unique invariant distribution because the Markov process is irreducible, and this is the unique invariant distribution. And we learn for free that the Markov process is in fact reversible. The random walk is reversible. Okay, so now we've found the invariant distribution. So if we define MT to be the invariant distribution multiplying the configuration, and if you do the matrix vector product, this is just some constant, 1 over twice the number of edges times the sum, and that's a martingale. And any multiple, constant multiple of a martingale is also a martingale. So this thing here is a martingale. Okay, and it's worth mentioning a couple of special cases. if G is what's a deregular graph? It's a graph in which every vertex has the same degree D. If that's the case, the degree of V is a constant, it's D, you can pull that out of the sum. And then this is saying that if you just take the sum over all vertices of its state, 0 or 1 is a martingale. So the number of vertices with opinion 1 is a martingale. Degree V is a constant, you can pull it out. It doesn't play a role. So we are summing over all vertices in V, the state which is 0 or 1 in the configuration. So we are counting the number of ones in a configuration. Okay, so if MT counts the number of ones in the configuration, then that's a martingale. That's the claim. And that's only true on a deregular graph. And we saw one particular example of this. We saw that on the complete graph, counting the number of ones is a martingale. And that's indeed a regular graph where every vertex has degree n-1, since it has an edge to every other vertex. Okay, so this picks up the Voter model on the complete graph as a special case, as it should. Okay, so we worked through those examples. Now let's go back to the question we started out with. So what's the probability of reaching consensus either on, say, the all one vector? To do that, we are going to use the optional stopping theorem again, and we are defining the random time t to be the first time that the voter model is either in the all zero state or the all one state. Okay, and this is a stopping time. That's easy to see. You can tell by looking at the process up to time little t whether it's already hit one of these states or not. Also, this random time t is finite with probability 1. If Q is irreducible, meaning G is strongly connected, because then these states are accessible from all other states, as we already saw, and it's a finite state Markov chain. So it cannot take infinitely long to hit these states, to reach these states. Okay, so T is a stopping time. It's finite almost surely. Let's define alpha to be the probability that we get absorbed in the all one state, meaning that the voter model hits the, or this should be a capital T, sorry, there's another typo. This is capital T. So alpha is the probability that at the stopping time we are in the all one state. And the only way to do that is if the voter model reaches the all one state before the all zero state. Okay, and now MT is pi times xt. Xt is a finite state Markov chain. Pi is a given vector. So the product of these two vectors is finite, is bounded. It's bounded between xt being the all zero or all one vectors. If xt is all zero, mt takes the value 0. If xt is all 1, mt is the sum of the elements of pi. Pi is a probability, so it's 1. So MT is bounded between 0 and 1. I should have said that before using the optional stopping theorem. So T is a finite stopping time. The martingale is bounded, so we can use the optional stopping theorem. And that tells us that the expected value of the martingale at the stopping time is the same as its initial value. So the expectation of pi times xt is the same as it was at time 0. If x naught is deterministic. This expectation is not relevant. It's just pi times x naught. But if we start in a random initial configuration, you should take the expectation with respect to that randomness. Okay, so now let's work these out and see if we can use that to calculate alpha. Okay, I haven't worked through the steps. I've done this quickly. Okay, so let's do that quickly. So what if xt, so x at the stopping time is either the all one vector or the all zero vector. Those are the only possible configurations. If it's the all one vector, then pi times the all one vector is the sum of the elements of pi, which is 1. Okay, but what's the probability? So alpha is the probability of reaching the all one state, and with this probability, the contribution to the expectation is 1. So this quantity here, maybe again I should switch to the whiteboard. Let me do that. Okay, so let me write a few things again. So t is the first time. So capital T is the stopping time. So it's the first time that the configuration is either all ones or all zeros. Okay, or maybe I'll put a vector sign under them. Okay, and we've defined alpha to be the probability that we reach consensus on all ones. So the configuration is all ones at this time, capital T, when it hits one of the absorbing states. So that's the definition of alpha. Now, we showed by the optional stopping theorem that the expectation of pi, the row vector pi times the column vector xt, is pi times x naught. Okay, let me make explicit all the vectors here. But what is the expectation of pi times xt? It's the probability that xt is the all one vector times, if xt is the all one vector, then pi times xt is 1 because it's the sum of the elements of pi, plus the probability that xt is the all zero vector times, what's the inner product of pi and the all zero vector? It's clearly 0. Okay, so it's the sum of these two things, and that's just the probability that xt is the all one vector, which we define to be alpha. Okay, so the expected value of the martingale at the stopping time is alpha, the probability that it hits the all one state. And so we've shown that alpha is pi times x naught. Okay, so let me stop sharing that and go back to the slides. Okay, so that's what we have here. So alpha is pi times x naught. Now, if you recall the de Groot model, there we started in some initial configuration which need not be 0, 1 valued. It could take any real values, but we saw there that we reached consensus on a number which was the inner product of pi and the vector of initial opinions. And here we have, instead we reach consensus. We can't reach consensus, we only reach consensus on 0 or 1, but not something in between. But the probability of reaching consensus on all ones is the same inner product pi times the initial value. And so we could ask the question, having seen what we saw in the de Groot model, could we have guessed the answer? Okay, this is not important, this is just a little bit extra. And it turns out that yes, we could have guessed the answer by looking at the expected values. And if you look at their expected values, this is a similar calculation to what we did for the Martingale. Then the vector of expected values satisfies this recursion. So the time derivative is q times the expectation. And then you can solve this explicitly. That essentially tells you that these expectations have to converge. So if you work out e to the qt, the dominant eigenvector of this is the all-one vector, and then so this has to converge to a multiple of the all-one vector. And by taking expectations, you can work out that C is this quantity, because expectations are conserved over time. So C has to be this thing. And then the expectation here, so xt goes to either all ones or all zeros. So the expectation here is either 1 with probability alpha and 0 with probability 1 minus alpha, and that should be the same as this. And so you get the same answer. Okay, I've said that quickly because it's not so important. What's important is this calculation here of reaching consensus on the all-one state, and the probability of that in terms of the initial conditions is the inner product of the invariant distribution and the initial configuration. Okay, I'm stopping here. So that's the end of this lecture. So we worked out here what the so we looked at the voter model on an arbitrary graph and worked out the probability that it reaches consensus on the all-one state. And next time we are going to look at how long it takes to reach consensus.